Hello and welcome to another WJEC A level physics question. This was from January 2010's Unit 1 and it was question 5, and it's mainly about resistivity, but there's a couple of other bits with it. I'll just remind you that all the electricity work is now in Unit 2. First part of the question asks us to draw a label diagram of the apparatus you could use to determine the relationship between the resistance and the length of a wire. I've already taken the liberty of drawing the diagram. I've gone for the simpler method of using an ohm meter with a movable contact and a fixed contact at the other end of the wire with a meter ruler nearby so that we can actually measure the length of the wire that we're finding a resistance of. The alternate method would be using a voltmeter and an ammeter. Nothing wrong with either method, just this one is simpler to draw and also simpler to talk about. The next part of the question asks us to state what measurements we need to make, and basically all we need to do is measure the resistance. I'll just call it R here at different lengths. In A2 physics, when you're preparing for the prac exam, you always got a plan to do at least 5 different readings here. So we'd probably do measurements of the resistance maybe every 20 centimeters for a meter, or maybe even better, every 10 centimeters for a meter. As well as this, if we're going to determine the resistivity of the metal, we need to know its cross-sectional area. And we don't measure the cross-sectional area, we measure the diameter. So let's put that down, we're going to measure the diameter. And we would use probably digital calipers or a micrometer. Next, the question asks us to explain how a value of the resistivity is determined from our measurements. Well, the best technique is to plot a graph of R against L first of all. So a little sketch of this at the bottom of the page. Resistance against length should be a straight line through the origin. Now if we compare the formula R equals rho L over A, given in our data books, to the formula for a straight line through the origin, Y equals mx, you can see that we've got resistance on the y-axis, length on the x-axis, so the gradient is going to be rho over A, and hence rho will be the gradient multiplied by A. And A is determined by pi r squared, but remember that we've measured a diameter, so it's pi times half of the diameter squared, or if you prefer, pi d squared over 4. And that's basically all we need. Say determine the gradient, multiply the gradient by the cross-sectional area, and then we've got the resistivity. On the next part of the question, we're asked about a strain gauge. Now, a strain gauge is basically a device that measures sort of small extensions or compressions in things like bridges and buildings. And what it is a strip of metal usually sort of glued onto some plastic or whatever, and it's then attached to the structure that we're trying to test. And there's a couple of connections to an electrical circuit to allow its resistance to be measured. Now when the structure extends, the wire in the strain gauge gets thinner and it also gets longer, and so its resistance changes. So using the resistivity equation, so once again R equals rho L over A, we've got to explain whether the resistance of the strain gauge increases or decreases when the structure extends. Well, let's look at each term separately. So if the resistivity is constant, which it is, and the cross-sectional area didn't change, then we could say that resistance was directly proportional to the length. And if the length increases, so does the resistance. If everything else was constant, in other words the resistivity and the length are constant, then resistance is proportional to 1 over A. So as the area increases, as the area decreases, we can see that the resistance increases. So perhaps I'll go back to that previous bit. So I'll just say L increases, so R increases as well. Now you notice that both factors lead to an increase in resistance. And that's our final answer there. On the next part of the question, we've got to calculate the resistivity of the metal in a strain gauge. So if we go back to our equation as it is in the data book and simply rearrange it, you'll get that rho is equal to RA over L. Just got to be a little bit careful here with units. So we're told that this material has got a resistance of 650 ohms. Its length is 32 centimeters or 0.32 meters or 32 times 10 to the minus 2 if you want to be careful about shifting decimal places. Oh, sorry, that's the area, sorry, the length, not the area. So let me just erase that a second and correct that. So put that length on the bottom, 0.32 meters. The cross-sectional area is found by multiplying the width and its thickness. So we've got 0.2 millimeters, so don't forget times 10 to the minus 3, and we've also got 0.0012 millimeters, also needing a 10 to the minus 3. So let's put those numbers into a calculator and see what we get. And here we get 4.9 times 10 to the minus 7. And don't forget the unit for resistivity is the ohm meter, not the ohm per meter. That would be about 49 times 10 to the minus 8. 10 to the minus 8 is a common power that's given for resistivities, and from a bit of general knowledge, I would guess that this material is supposed to be constant tan, which has that sort of resistivity in it. The last part of the question uses that strain gauge in a potential divider circuit. And it says the change in resistance of a strain gauge is monitored using a potential divider circuit. The strain gauge is placed in a series with a fixed resistor R as shown. You've got to calculate the value of R, which will give a PD of 1.6 volts across that strain gauge. So various ways of doing it. We can use the potential divider formula, or we can just use some basic physics here. So let's do the basic physics way. The current flowing through that circuit will be the potential difference divided by the resistance. So we've got a 1.6 volts over a 650 ohm resistor. So that would calculate the current in the circuit for us. Now that comes out as about 2.5 milliamps. But I'm going to use the exact value in the rest of the calculations. Now if there's 1.6 volts across the strain gauge and there's an input of 6 volts, then the PD across R will be 6 minus 1.6, which will be 4.4 volts. So now we can work out the resistance of R by doing 4.4 over that 2.5 milliamps that we've just worked out. And this ends up with us about 1790 ohms. If instead we want to use the potential divider formula, which is V out over V in, equals R over R total, then here we have V out is 1.6 volts, V in is 6 volts. R, the resistance where the output is 650 ohms, and R total is 650 ohms plus the unknown resistor R. So if we do a little bit of cross multiplying, we'll have 1.6 times 650 plus R equals 6 times 650. So a little bit of work on a calculator. So we have 1040 plus 1.6 R is 3900. So 1.6 R would be 3900 minus 1040. Which will be 2860. And therefore R is 2860 over 1.6. Again, given us 1790 ohms. Thank you very much for listening. Please remember to like and subscribe.